Hello. I'm going to apologize ahead of time because I am feeling a little under the weather. But, so what we can start with is a free body diagram. You'd start with being a little bit rude and putting Caleb down to just a block of his mass, the 70 kilograms. Since gravity acts straight down, you can add his weight going straight down. We have the size of mg. The other force at play, well, there's two other forces at play. The other force would be his normal force because he's skiing down a surface. So you would draw that in. I would usually have it drawn through, going through what we'd be calling his center of mass. I'd have some magnitude n. The last force at play is going to be his friction force while he's along that surface. And I'll draw it going along the surface, but since he's going down the slope, friction would be applied up the slope. I'm going to call that the force of friction. So that would be your part A. It would be just drawing the block, showing that the normal force there, and showing that it is perpendicular to the surface, as all normal forces should be. Perpendicular. The gravity acting straight down, and friction force being parallel along the surface. The speed at the bottom. The simplest way to apply that is to work with energy that you would actually be starting all with a potential energy of mgh and then come down at the bottom of the slope with his kinetic, assuming that no other funkiness is in play. Mass is on both sides, so that's irregardless. Multiply by 2 and square root both sides, and you find out that speed at the bottom is going to be equal to square root of twice g times h. And I didn't plug those values in ahead of time, but that is what it's going to end up being by the time he's at the bottom. To find out his acceleration, you'd actually be able to work with the values and directions in this figure here, with one change that I would make. It is really hard sometimes to work with these principal drawings where you're showing the block sliding at an angle down on the surface. I tend, instead of looking at that, I look at pictures more like this, where you redraw it and your normal force is still the perpendicular, your friction is still that parallel, and then now gravity in the picture acts at an angle, but still in the real world still acts straight down. But now the angle that is in between here, that is that same 30 degrees that was over here, is also over here. So to figure out what your n is, you'd be able to say, okay, well, the block is not going to fly upward off of the surface. So the forces perpendicular to the surface have to sum to 0. Normal is straight up. Gravity acts with the adjacent side, so that'd be ng cosine of theta. And then that step-by-step thing would just say the normal force is mg cosine theta. Again, I didn't plug these values in ahead of time. You'd be able to evaluate it. That'd be your normal force. And then off of knowing your normal force, friction force is equal to your coefficient of friction times your normal force, which we already have something to substitute that in. I'd be able to give you your friction force value. And then off of that, you have to do the forces and accelerations in the x direction, where there's going to be some acceleration along that path. Gravity in this instance is helping you get down the slope, and friction is trying to stop you. The next step on that one would be to replace anything that we can, where we have everything to replace friction with the, what is it, mu mg cos theta. Mass is everywhere, so m's can just cancel off. You divide by m on both sides. And your final equation for figuring out the acceleration would then be a is equal to g sine theta minus mu times cosine times g cosine theta. So that, again, I haven't plugged these values in, but you'd be able to easily evaluate that and get your numerical value. The bottom of the slope, he encounters a horizontal surface with a coefficient of kinetic friction of 0.5. What's his acceleration on the horizontal surface when he comes to rest? Surprisingly enough, that equation that just got solved for here applies on a flat surface as well, because theta would just be 0. So you can plug 0 in there, 0 in there. G is going to be same G. Mu is going to be that new 0.5, and you'd be able to find out it's going to have the negative acceleration of negative mu g on that surface. So that's kind of a little cheat around. If the teacher or professor is asking for more work, you could go through and show that the forces on a flat surface solve down to that, where n is just going to be mg, not mg cosine. Then friction would be mu mg, and then this whole solution process that we went through here, but then along a flat surface. And how far does it travel before coming to rest? Well, that is going to take into account that we have an initial velocity on that flat surface. We have an acceleration on the flat surface of the negative mu g. And then you can use the kinematic equation at the final velocity squared to do this equation here. So we would have our acceleration of being, so we want it to come to rest. We know what our initial velocity was, and then we're squaring it, so it's going to be 2gh twice of negative mu g and whatever our distance is. So moving those around, canceling 2's, canceling g's, should get you to a point of the distance that it'll take you is going to be h over mu, which h is just a consequence from the prior height of where the where the skier was originally at. It's not really that you can change your, I mean, you kind of can change your sliding distance, but it arose because our final velocity, our initial velocity, was coming from the square root 2gh, which came from our energy thing of this system problem. I hope that helped. You can message me directly on the tutoring site if you would require any further assistance or any more questions on this type of question. Hope you have a good day.